Let's talk about the actual errors that we're working with. So the training error, so that's the error that you get on the training set. And the general form for the training set, the general form for the training error is something like this. So you're going to sum up over all training examples the individual errors that you get for each example xi, right? So what is the error? Xi is the input that we get. Fd of xi, that's our prediction. That's what our classifier or regression system predicts as the output for xi. Yi is the true value that should have gone to xi, right? So maybe we predicted spam and it was not spam. And then the error function is some measure, this error inside, is some measure that tells you, how close was the predicted value to the true value. So in the simplest case, when in classification, it usually just measures were they the same or were they not the same. Did I predict the right class? When you're doing regression, the output of a predictor and the true value, they're real numbers. So it makes no sense to ask, are they the same or not the same? So you take some measure of difference between the two. Maybe a squared difference or absolute difference. And we'll talk about the variance of that. But overall, that is the training error. And the sum is over the training set. So what is the generalization error? The generalization, that is how well you do on the data that you don't have today, on the data that's going to come tomorrow. And the problem with that is you don't really know what tomorrow's data will look like, so you don't know what xi's will be, and you don't of course know what labels they will have. Otherwise, if you did, there wouldn't be much need in predicting those values, so you wouldn't be building a classifier in the first place. But you can still come up with an equation for the generalization error because you know the ranges, right? So you know the possible range of x's and you know the possible range of y's. So if you're recognizing digits, for example, the x's are the bitmaps. So they're 20 by 20, let's say binary bitmaps, and there's only a fixed number of them, right? You could enumerate them. There's a lot, but it's a finite number. And the y, there's only 10 possible values. So we can actually write down an equation for a generalization error, and that's what it would look like. It looks pretty much like the training error, but with few important differences, right? So, okay, well, let's take it step by step. So instead of a summation, we're going to have an integral, and that integral goes over all possible x's and all possible y's. And why it's an integral and not a sum, in the case of 20 by 20 bitmaps, it would actually be a sum, because there's a finite number of them. When you have real valued data, it's not a sum. You need to integrate over all possible values for every possible attribute. So that integral really captures every possible value of every attribute over all the possible classes that you're trying to predict. So that's a really big space. This P of yx, that's how often you expect to see a particular value x and a particular label y together in the future. And so that's a probability distribution for the future data coming down the line. And that's the error, which is defined in the same way as we had it before, right? So we have the y, the x, our function f, the predictor, would compute some value for the x, and then we see, was that the same as the true label or something else. So that's the equation for the generalization error. It's typically always greater than the training error, and you can never ever compute this thing. Why can you not compute it? So in this whole formula, there's basically only one part that we don't have. And if we had it, we could compute the thing. So, sorry? Yay. So it's this probability. That's the only bit that you're missing. Because that tells you what data is going to come in the future and what labels it's going to have. It's all pretty much embedded in there. So if you could compute that number, then you could compute the generalization error. And that might give you a hint for why so many machine learning methods are probabilistic. And so many machine learning methods, they really just work on estimating a joint distribution of classes and observations, because that's at the core of what you're trying to get out of your system.